Yeah, this is the last lecture of 2160, lecture 25. The title is the dual faceted linearization with application to nonlinear model predictive control. So just to think about the things we have been doing. Yeah, 2160's the second half in particular is really focusing on the system representation and the identifications. And the one side that, in particular for linear systems and identifications, will take the materials from system dynamics and controls, and then also blended that with the machine learning, dealing with the nonlinear systems, and kind of underpinning mathematics we've been using extensively, the statistics, and then a particular part of Hilbert space. So now, kind of reflections, looking at the history of all engineering and then control engineering in particular. Obviously, modeling and representation are the foundations of engineering. First, you must be able to represent, right? So that's actually important, and not just for pattern pain analysis, but for computational analysis and modeling and representation is a cornerstone. Now, specifically in the control engineering, if you look about the history, it's just kind of a big picture of that. Some groundbreaking progress were made, and when the control engineers found a new representation methods, such as first frequency domain representation, the body plots and the Nyquist plots, and that's actually one type of representation with it, and a bunch of classical control techniques developed, right? And then people found the state space representation will be more appropriate for digital, computing, and actually, as you can see, that tremendous progress was made with the state representation. And I'm hoping that the linearization of nonlinear dynamics through lifting could be one of the new representations leading to groundbreaking progress for the future. There's a lot of, kind of a, new trend in the system dynamics and controls, but it's actually having pretty good, ground in many fields, including machine learning. So now look at the lifting techniques. To my knowledge, the first paper dealing with the lifting through chrono methods applied to classification programs was made by Thomas Kovar. Kovar's vintage paper back 1965. To me, that's the first to address the use of kernel methods in machine learning, given a set of training data that is not linearly separable, but one can recast the feature space to a higher dimensional space through kernels. You can solve the programs, right? The Kovar's problem and classifications are basically dealing with at the end of the day, you care only the signs and then dealing with the inequality equations. Now going to regressions, you have to deal with the equality, and then that needs a different set of mathematical tools. And then the origin was basically the Koopman's work about 1931, and given we just limit our discussion to discrete time, although continuous time is, natural extensions. But let's focus on the discrete time because that's better connected to kind of tools that you familiar with, and the data-driven method. Okay, so capital F is a nonlinear map. This is a pointwise map from xt to xt plus 1. And we assume that F is non-singular. And also we consider observables. Now, this is the scalar valued function. Rn to R. And we consider, their time trajectories, starting from the time 0, moving to the next point, So yeah, the Koopman operator in a discrete time is defined to be the following map. So observables are actually in the Hilbert space, and then this Koopman operator, Hilbert space to Hilbert space, associated with some specific pointwise map Frn to Rn, is the actually linear transform that satisfies the following relationship. So K, you can think about the kind of a big matrix times GK, GX equal G composition with Fx, and this one applies to axion functions such as trajectories. Okay, the original, although the original systems represented as a pointwise transformation is nonlinear, but above Koopman operator is linear. So that's actually an important part. So just to highlight the difference and characterize this, one discrete time system that we can use some matrix representation. So but time-wise transition, we call that the evolution-based operator, or we can write it in this way. We cannot write it in a traditional matrix form in a beyond this point. However, when the Koopman operator is used, it can be extended this way. But major difference is that here in the upper part is the xt is mapped to in the next state, right? And then actually observed from G1 functions, and then that's going to this one. But here the transition is made for the entire trajectory. So G0, Gi 0, 1, 2, 3. This one may be going on infinitely. Mapped to the next state is basically through this infinitely large matrix. Now, the computations, and then we discussed the computations through a companion matrix. And this may be easier to consider than the dealing with the function transform directory. So we put together, as usual, all the data Z, and then the 0 to n minus 1 and the 1 to n. And interestingly, these two sets are connected through. This one is placed in the Koopman style. It turns out in the matrix connecting these two, the companion matrix, and this one is just a one-time slide. And the important part is the last part, last row that is written here separately. So what you need to do is to generate the last the states observed from observables G1 to Gm are basically created as linear functions of the previous observables. And some rank condition must be met so that the solution exists to this. We set the m to be pretty large in a number, and generally that there's no actually rank conditions met. So it turns out that we have some residue errors. And what we need to do is best approximation is to make this residue difference to be minimum. And then that's actually given by this least square representation. And this residue, sum of squares residues indicate some accuracy of the approximations. Now, one interesting question, extending this is basically, as m, this guy, is extended to tend to infinity, whether this error goes to 0. In other words, this one converges to 0. And in fact, if all observables that we use here are in Hilbert space, Hilbert space, perhaps some of you know that the all Cauchy sequences converge within, and at some point within the Hilbert space. If that condition is met, this residual sequence converges to 0, and then we get the closed form representation. So far, exact linear models have been found for some class of systems already. And one is obviously the original Koopman's work that was actually applied to Hamiltonian systems. These systems are represented in terms of the positions and the momentum. If the system has that particular structure, he found exact linear models for that. And then later, people worked on that quite extensively. And nonlinear autonomous systems having a single equilibrium or a single attractor or the limit cycle, also a single torus. It is known that the nonlinear autonomous systems can be represented exactly with the linear expressions. If you have multiple equilibrium in the space, obviously that one is actually a little different topologically. And so far, the method is not successful to exactly linearize the systems. Yeah, that's fundamental topological limitations and exist in that. But this area is actually both mathematicians and people from the different fields have been working on that. Maybe some of the important breakthroughs being made somewhere. And another reason why we look at the data matrix representations is that that's actually from that matrix we can easily obtain eigenvalues and then eigenvectors of Koopman operator, and that gives us a very good interpretation of the temporal behaviors of those observable functions, and then eigenvalues in particular, lambdas. So any the observables can be decomposed to a extended to eigenfunctions and eigenvalues and the modes that these are obtained from those Ritz values and Ritz vectors applied to companion matrix, as I explained. And then easily we can find the behaviors of those. Now, with the use of the lambdas, if lambda is actually this is basically a complex number, and then just as you have learned for model the decompositions of linear systems, we can decompose it to multiple modes. And if one of the modes and having the bad guys eigenvalues greater than 1, that's basically diverge, well within the 1 and converge, and even kind of limit cycle can be represented. There's a case where lambda sitting on the unit circle. Also, from this eigenvalues, a series of eigenvalues, we can actually truncate the systems because faster, quickly decaying modes, very, very fast modes. Just a few seconds later, it just disappears. So you can actually ignore those modes. So that allows you to truncate the systems so that even though the original system is basically infinite in order, but you can truncate it safely, containing the all major modes and then ignoring the minor modes, which are not actually significant in terms of the accuracy. So let me see. That's actually the last time we did go very quickly. So that's a quick recap and then a little bit in addition to that. If you have any questions or something that you'd like to raise, please ask any questions. If that's okay, I go to the next part. Yeah. Okay. So yeah, and then also please, stop me and raise any questions anytime during the following, talk. So drawbacks and still open questions of the Koopman operator theory. So needless to say, Koopman operator, so for exact linearization is applicable only to autonomous systems with no control inputs. And then many of you are taking an aside at this point, it's not applicable to control systems. So what's the point? And for exact linearization, the system must be lifted to an infinite dimensional space, which is also another disappointing part. Although, as I said, we can truncate it, and there are so many techniques that we can get rid of this problem in a practical sense. But for exact analysis, that's actually the major hurdle. And also more practical limitation is that there's no systematic method for finding an effective set of observables. Typically, it requires a trial and error effort to find good collections of observable functions. And so some basically arts are involved in this stage. So goals and the needs for research, it's being done by many groups. Is to establish a methodology of lifting linearization for non-autonomous systems having controls. And number two, keep the order of a lifted system low, yet accurate enough to predict the true dynamic behavior over a required period of time. It's impossible to build the perfect systems that can actually go forever perfectly. But if you limit to some actually, how to say, shelf life or limited the time span when the system must behave very properly, accurately, then actually it is usable. And then thirdly, make the lifted dynamic system causal and physically meaningful. This last part is actually one of the focal point of this is the part of today's lecture. That's if we introduce any just manipulating mathematics and then those observables oftentimes having no physical sense, and so that's actually bad. So how can I actually make a connection to physical world is another problem. And then also the causality is a very important issue which we will discuss. Okay. So what we'd like to do is something, the representation readily usable for controls. So original nonlinear state equations is something dx dt equal fx and the input to u. And we're lifting the systems to the one having the original independent state variables as well as additional variables, which we call auxiliary variables. This is one particular type of observable. So although we do not actually assume it must be in Hilbert space and so forth, but some additional variables, auxiliary variables, are to be integrated into the independent state variables. So we have two types of state equations, dx dt, which is actually linear equations, and the eta dt lifting the dynamics. Eta is to be treated the additional state variables, so we have to have state equations for that. The eta dt is not only the functions of x, but also eta and the input to u. Okay. So now let me start with some bad things and you should not do, and it's a very unique issues when we incorporate an input to u. So dx dt equal fxu, right? So that, one example like x dot equal ax cube plus bux. Okay, and then naively, if we just replace, say x cube by eta 1, and this time ux by eta 2, you got the troubles. Of course, x dot, this equation can be represented as just a apparently linear expression like this, a eta 1 plus b eta 2, sounds great. However, you have to add two additional differential equations, one with respect to eta 1, the other is with respect to eta 2, right? And troubles comes with the eta 2. If you just differentiate eta 2 with respect to time, since eta 2 is a product between the two, so partial eta 2, partial x dx dt, plus partial eta 2, partial u, and then du dt. And so it does include x dot and u dot. Well, x dot is okay. X dot is basically replaced by this. So eta 1, eta 2, basically extended state variables comes after this. But the real problem is u dot. Have you ever seen the state equation, and not the actual transfer function, state equations including u dot in it? No, that's not the state equations. The state, given the current state and then input to you must be able to predict in the next state, right? But if you include the u dot on the right-hand side, then you are in a sense using the future information. So you cannot take the derivative of input to u. So this naive method doesn't work. It's just a replacement. This one doesn't work. Okay, so this is one critical issue when you deal with the non-autonomous systems and lifting dynamics with the new variables. But the new variables includes or somehow related to the input that you must be careful not to violate the causality issue. So the techniques I'd like to introduce today is called the dual faceted linearization. It is the work I've been working on in the last 5-6 years, and a schematic method for finding a dual causal observables or auxiliary variables. We use this word observables and auxiliary variables and in an exchangeable manner. And these variables are for lifting linearization of non-autonomous systems. So two equations are dx dt, and then it turns out that this equation is actually exact, no approximations involved. And the second equation, so d eta dt, is actually additional approximated differential equations, but having some good properties in it. It must be accurate and low dimensional. And the low dimension is actually achieved because we don't need many etas. And then accuracy is another interesting point. Excuse me. One of the primary applications we're going to discuss today is model predictive control. So some of you already know the model predictive control, which I explained later, is to solve the optimal control within the some given time horizon for the future. So the model that we have to use is to be valid for the certain fixed time period, time horizon. So this method, although it is a approximation, however, it is actually valid for a certain time period from now on. So we look at this kind of application areas and actually determine the accuracy needed for solving the problem. So and also it is low dimensional, so it's appropriate for low, real-time computation, and then actually applied to model predictive control. Yeah, so actually, it's nice to reduce the originally nonlinear model predictive control, reduce to a linear model predictive control, makes it much, much easier, such as the convex optimization. So the outline is bring in the physical insight into the selections of observables and auxiliary variables, and the physical system modeling theory is to be brought in, and the definitions of auxiliary variables are given, and the linear regression of auxiliary state equations will be derived as a second state equation, and I will give you some of the numerical examples, and then apply this one to model predictive control. Okay, and then we do some comparison to Koopman operator. Now the following talks, following part is based on the kind of plenary lecture I gave at the American Control Conference 3 years ago. This is actually a big control conference, and then that was the time I just presented this one, and I took the slides from that talk. So the title was towards the new modeling methodology for nonlinear dynamical systems and lifted the dynamics, data, and the physics. That's the physics is the important part. So the first, the take-home message is physical systems are linear in its own structure. So basic elements like mass, spring, dampers in the case of mechanical systems, they are linearly connected in all dynamical systems. So we are mechanical engineering, and I know not just math, but we have some physical knowledge, and how can I actually incorporate our strengths into these areas. Now, if you recall, I think everyone knows the Kirchhoff voltage law and the Kirchhoff current law. It is interesting to note because, if you look at the, any circuit and then look at the closed loop, and all voltage across this closed loop sums to 0, right? And then the current at any point basically sums to 0. Very simple, principle. And the data, it is actually extended to some energy domain by the Telegens theorem. But I know this is very fundamental principle. When you look at the physical network, these two principles, must be applied. Now, one interesting extension was made by Professor Henry Painter. He was a professor of mechanical engineering in our department. And I know him, and I was influenced by him some way. So I know his actually most important contribution is general physical system modeling theory. It's called the bond graph. And let me just spend just a couple of minutes to explain this. This is to give us a good insight into how we can actually introduce how we can find the observables in a way that is useful for our lifting dynamics. So in the bond graph, we have subsystems A, subsystem B's. They are interacting energetically. And such connection can be described by the flow of power. And the power is a product of two variables all the time. In the mechanical domain, it's a force times velocity, it's a power. In the electrical domain, voltage times current, the power. And the fluidic flow, pressure times flow rate, I'm talking about the incompressible flow, turns out to be power. So these two variables are used to represent the behaviors of those dynamical systems. And then he used the a more generic term. It's called effort for force, velocity, and pressure, and the flow for voltage, current, and then the flow rate. Now, Kirchhoff voltage law and then Kirchhoff current law can be represented in a more generic form by using the bond graph. And the Kirchhoff voltage law is actually replaced by just a very simple notation, one junction. And Kirchhoff current law, or current sum to zero, is represented in generic term, a zero junction. So all the currents comes to all the elements and branches of this connected to this zero junctions. If you take the summation of the all currents, sum to zero, including these signs. And then this one's a little bit harder to imagine, but this loop is represented by just a single point, one junction, and then all the voltage of the elements come to this point. If you take the summation of them, it basically sums to zero. And the other side of the variables are effort versus flow. The flow here is a common, and then at the Kirchhoff current law, voltage basically remain the same. Voltage E remain the same. The other side is sum to zero. Okay, interestingly, this one applies to all energy domain, not only electric domain, but also mechanical domain. These two systems look very different, but if you represent in the bond graph, they are identical. So a bond graph is general, applicable to all multiple energy domains. And then actually, if you look at the this one junction, and all the here the voltage sum to zero, this one, and then in this case, all the forces sum to zero. And in mechanical domain, F minus something. This one is nothing but the Newton's equation of motion. That's actually equivalent to voltage law in electric engineering. And then now what is interesting here is that all junction conditions, so you have to write out these equations for every junction, Kirchhoff voltage law and current law in a generalized sense. They're all sum to zero, right? So they are basically linear conditions. All the junction conditions are linear. So connection versus elements property, this is a very important part. So if you write just one junction condition equation of motion, you get these equations, right? E1 is the voltage or force coming from one element, in this case, nonlinear spring C. Now, this E1 is output from this spring. So as it comes to that, one junction. Well, if behind this, E1 is connected to a displacement, and as you can see here, displacement, and the relationship may be nonlinear, right? But if you do not replace E1 by Q, which is nonlinear function, the original equation is basically linear because it's something sum to zero, right? And then given any kind of complex systems like this, we first identified all the nonlinear elements involved in it, and then identified the outputs from these nonlinear elements. And then what is the input and output shown here is basically a little bit the tricky part, and using this theory bond graph, you can find uniquely, systematically, what are output variables. But suppose we can find the output variables of all the nonlinear elements. We define a complete set of auxiliary variables to be all the output variables from all the nonlinear elements. Don't include any linear elements, but all the nonlinear elements produce some kind of output which are to be taken as auxiliary variables, observables. If we do so, one interesting point is that with these auxiliary variables, all the junction conditions can be written as linear equations, as I shown, right? Sum to zero. And then if any auxiliary variables is missing, if you don't actually include the E1 here, you cannot actually write the junction conditions in a linear form. So if you pick all the outputs of the nonlinear elements, that's actually sufficient. And that's actually necessary. So this is the minimum set of basically auxiliary variables to write the linear equations with the use of additional variables. So we can prove that if the systems are given and we know the connection among them, you don't need to know the relation and nonlinear functions of individual nonlinear elements, but I know, and we assume that we have some ideas about the connection about these elements, which is mostly the case. Then we can immediately write out the linear equations using the auxiliary variables coming from the nonlinear elements and the output. So now that is one side. And the other side is as we include the eta as the additional state variables. Now, in addition to dx dt, we need to introduce the differential equations or state equation for this eta value, right? Eta values. So if I take a very naive method, if just to take the Taylor expansion, first order Taylor expansion, we get eta dot equal Jacobian J times x dot, right? Here Jacobian Jx is basically partial eta of a partial x, and maybe I should write the dx, the d eta dx, and and times the x dot, right? Now usually what you do is basically linearize this Jacobian by evaluating it at a certain point, such as the x bar, or more sophisticated techniques. It's called the statistical linearization, and collect the data and then actually do some best fit for this j, and then pick that particular value of j, j bar. So whatever the method you fix the j, the result is eta dot equal j bar x dot. So what comes into your mind when you look at this? Eta dot equal some fixed matrix, j bar times x dot. Well, I know this indicate that the eta dot and x dot are collinear, right? Collinear. In fact, in place of x dot, you can actually substitute this one into that, and then what you get is this equation. But this equation doesn't provide any new information, because this is x dot and eta dot are actually collinear. Just the relationship is a linear relationship. It does not provide any additional information. Just the first equation is just good enough. So that's bad. So we need to do a little bit more, proper job. And here's the lifting linearization comes in. Yeah, but that's first to treat the situation that all the auxiliary variables are functions of x alone, not including the u. In case u is involved, that actually becomes a non-causal situation. So we have to treat it differently. So suppose easy case, this one, eta x, right? Then what you can do is that, instead of just, naively and use the Jacobian and fix it, but you can, introduce the linear regression, at least, linear regression. So eta dot is basically, regress on not only, x, but also eta and then u. Right, and then you can find these quotient matrices hx, h eta, hu, so that this one can best predict the eta dot and the hat. So lifting linearizations, this is just a standard least square problem, right? So you have a predicted one versus a correct one, and you can just solve this problem. Maybe you can put them together, these three matrices, into just one matrix. Accordingly, you have to put together variables x, eta, u into this kind of big vector, say C, right? And then you collect the data, and then actually you can solve the least square estimate in this. Okay. Now, just to think about it, under what the conditions you get the unique solutions? This actually least square is basically unique solutions. It's convex optimization, right? Under what the condition that this can be obtained? Yeah, here's interesting observation we can make. The data matrix that we use for this computation, let's say C1, C, each of them have X, eta, and then input use in U, right? So we just concatenated this in this way. So this one is actually a data matrix, right? So first of all, it must be persistently exciting, right? And more specifically, yeah, no feedback is allowed between X and U. In particular, linear state feedback is allowed. So if the data is taken from a closed loop system with the state feedback U equal K times X, for instance, U and X are collinear, right? So the rank of this one is basically deficit. Rank deficit situation happens. So you can't get the unique solution like this, right? So this one is a very similar story to the subspace method. And I don't think you remember that, but one critical condition for enforced subsystem identification requires these conditions. Please take the data from open loop. No, state feedback is allowed. And the third condition is interesting. All the elements must be nonlinear. Okay. That said, that eta, which is actually auxiliary variables, observables, we defined as output from the nonlinear elements. Instead, if eta is actually some element turns out to be linear, okay, but it's a sneak, you by mistake include that element as auxiliary variables here. That variables is basically linear. That means that it's a linear function of X. So eta and X are again collinear. So putting this one in this way, this is not the full rank, right? So you can't get the unique solutions. So by checking the rank conditions, you can actually determine whether or not you have collected the right set of data to do this job. Okay, so if we do that, we get the optimum solutions, and we can get the full actually regulations like this. Now, interesting question is that we started with the naive method, right? With the use actually of fixed Jacobian J bar, right? So interestingly, the prediction capability predicting eta dot, this versus this, which one is more accurate? Well, this is the approximation because this is evaluated at this fixed point, right? This one is basically use of regulation, linear regulations. But you see that this one has more parameters to tune than this. So officially, we can actually prove that the method that we described using this lifted dynamics, hxx, h eta eta plus hu having three kinds of parameters, that actually prediction error is basically smaller than the prediction error by this Jacobian. We can prove that, and that's simply because parametric tuning, the dimensions are very different. So this one provides much better results, and then this guy is just one special case of this global case. Okay. Yep. So now, just a little bit of reflection. So we, introduced the, kind of weird additional state variables, right? So dx dt, and also d eta dt is also involved. Does this really make sense? So this argument, this example illustrate the situation. So suppose we have a linear system, and transformation of state variables does not change the structure of the state equation. For instance, actually, so if we have f equal minus kx, just a simple linear spring problem, and then the state equations using x and the one with the f are basically the same. So f equal ma, we can get this equations, right? Now, one way is to use the state variables x. You can represent it this way. The other way, if we use an output side of this linear element f, use f as the independent variables to describe the system. Yeah, we can write it this way, right? Just to replace x by f, we can write it this way. But these two equations are exactly the same. So there's no point to use the two representation of the equations, one with respect to independent state variables, original state variables. The other is by actually this an output side of this element. However, that is not the case when you deal with the nonlinear springs like this, f equal minus ax minus b x cubed, okay? And nonlinear springs. Because one way is to represent this with respect to x, you get these equations, right? And you can try to represent this equation by using f. Of course, a and b must be positive to make it actually invertible. But under that condition, if x can be written as a nonlinear function of f. So substituting that one into this, what you get is this weird equations. Okay, this one is basically the same equation as this, but we represent it by with use of output side of this nonlinear element. That's actually force f is used here. Okay, so seemingly very different forms of two equations representing the same nonlinear systems have been obtained. Well, here I have to use the derivatives of this nonlinear function, and that's actually nonlinear function g. Inverse to this nonlinear function, the x equal g of f, and then I took the derivatives and of this, that's needed up to second order, so we can write it this way. No one wants to do this, actually represent this in a more complex equation than this, but I know this expression is meaningful when you have a nonlinear systems and you represent the systems not only with respect to one variable x, but also the other variables eta, and then and when in particular when you linearize this, these two set of equations represent things in a very different ways, and they get the different linear equations. So the situations are like this. We see the nonlinear systems. This is complex, but viewing that from two, set of variables. One is actually original state. The other is the other side is auxiliary variables, observables, and each result in the different state equations in here. So we lifted the systems, and this is more informative than the original, just simple naive linearization. X and eta, it's as far as you look at these two equations, they are basically linear equations. But behind this, eta and x are related through nonlinear transformation. But this one is not involved. It's not actually visible as far as you deal with these two equations. Okay, before going to the numerical example, any questions or anything to clarify? So this is a way of finding, useful observables. So in a sense, within the large framework of the Koopman lifting linearization. Yeah, but I know we engineers knows what are actually how the systems are connected, and then particularly interesting is that the system connection itself is basically linear. In other words, any kind of engineering systems, electric circuits or mechanical systems, we represent the systems in a way that the individual elements are connected linearly. So we can exploit that one. And then one set of equations are totally, rigorous, exact. The other side, so you introduce the new variables, and that must be, lifted to have some dynamics. And then we introduce some, approximations. But that approximation is basically fundamentally much better than the approximation you have been using, such as the Taylor expansion. So that's actually the excuse me, some question. Yeah, so I never have asking a very fundamental important questions. How do you know the accuracy? That's actually, whenever we step into some approximation side, which is necessary going beyond the Koopman. We had to do some levels of approximation, and actually how accurate is a critical issues. And there are several actually techniques being developed. But it's still very early stage. I would say almost no practically useful method. And some attempt is within the framework of robust control. So we can actually, if we can set some kind of upper bound that can be used for the control design and so forth. But this area is so very much changing almost every month whenever new papers being presented. So let me just emphasize some of the effectiveness of this. So numerical examples and applications. So one particular, one of our former sponsors, it's basically construction machinery at the companies, and we learned a lot. And then, this one is basically earth moving. Talking about the excavators and dump trucks. We basically look down on this kind of work and dealing with the dirt. It's a dirty work. It's hard to convince my students, and this is a really interesting problem. But as we do it over some time, this is interesting because the system is very complex. Dealing with the rigid body is very simple, but dealing with the dirt, that's really, really complex, right? So this is actually the former TA of the 2160, Philippos Sotiropoulos, and he was actually the key person working on that. So this is the excavations, and you have to deal with the soil like this. Soil is difficult to model. It's actually a mixture of ugly damping, and then inertia changes as you lift more the stuff, and then very much distributed behavior. It's so hard to model. On the other hand, the machine has hydraulic systems, and fluid thermal systems are very much nonlinear, right? And then so it's a bunch of nonlinear systems are harder to model. So we built some kind of simplified dynamic model of the excavations, the bucket interacting with the soil, and then we identify, we know the kind of structure, here's the chunk of a mass, here's the chunk of resistive elements involved. So we know the structure and how those elements are related. So based on that, we can draw the bond graph like this, right? Now this actually, nonlinear functions involved in each element is a little bit academic exercise, but I know we make it very drastic nonlinearity, such as this, damping element and spring elements is actually going the back, negative side of the slope. So very highly nonlinear. Okay, And then we identified all nonlinear elements and identified the outputs from these elements. And then these are the auxiliary variables, observables, right? And then we put them together on original state variables plus auxiliary variables. We have 4 elements, 4 auxiliary variables reflecting 4 nonlinear elements involved in the systems. And then we did go through this analysis, and it turns out that the prediction of the first equation, x dx dt, that's the exact equation, so don't worry. In a problem comes in from the second state equation, d eta dt, and then prediction accuracy is very important part, right? So, we use this, root mean square error of actual prediction eta dot, this metric. And we compared 3 methods. This is actually dual facet linearization. This is normalized to 1. And then theta expansion, naive one, actually 11 times a bigger error than the dual facet linearization. And the statistical linearization, this is a little bit better method, classical, but better method. It's still almost 3.5 worse than the dual facet linearization. And a very interesting point is that, of course, this is actually an approximation. So, your open loop simulator, originally starting with the same correct value, but predicted the state is to deviate as you push a certain time, right? So this is the way I evaluated the accuracy of the systems. So let's first set some propagation time, okay? And this, black solid line is the true trajectory of the original nonlinear systems, right? And then from any point along this line, you start with your approximation, and the dual facet linearization (DFL). Open loop simulation kicks in from here. Let's say starting with the correct value, but it tends to deviate, right? So over some fixed given time period, where this one is going, how far is it from this true value? And so we provided this propagation time, and then evaluated the maximum error, basically creating the envelope of the error band. So here's the results. Okay, so again, the black line is the correct one. This is one of the state variables, P1. And if we use the theta expansion, starting with any point along this x value, sometime later, it is deviate to this actually extent, blue lines. So it has a pretty short, shelf life. Immediately after that, it's okay, but after some point, it is deviate very badly, right? Statistical linearization, which is a relatively better method, there's still significant error here. But dual facet linearizations, this dotted green line, the method I propose is basically going this way. So very good, accuracy has been guaranteed. So this one is basically given some, fixed time period, this model is valid. So what comes into your mind, when you are given this kind of a model? Yeah, surely we can use this for model predictive control, right? Model predictive control is a type of optimal control. But we look at the finite time horizon. So starting here, current state is here, over the following capital T second, we like to optimize some of the performance index like this. We like to find the control input to achieve this. And then we basically execute only the first segment of this control. So this is to give you some UT plus 1, UT plus 2 for the future, but we execute only UT current step. But I know that UT is actually is basically good, the part of the optimization here is consistent with the future, best trajectory. So we executed that one. And then the next time step, we set the time horizon for the next actually capital T, and then recompute this again, and then execute for the first control, optimal control at the UT at that time. And then we cycle through this one forever. So we don't care the future trend over here, but we focus on some meaningful time horizon and solve this one repeatedly. The challenge is that you have to compute this and very quickly, because this is actually every time cycle, so you have to compute it, right? So it must be very, computational efficiency is needed. On the other hand, the modeling side, you need some valid model over some time T, but not forever. So this kind of lifting linearization really makes sense. If you use the nonlinear model predictive control, there are many computation method is available, but it's a hard problem, very computationally expensive. And then also bottom line is that the local minima problem comes out. So even though you get the some solutions, but that is not the globally optimal. But if you use the DFL lifted linearizations, that is actually linear systems here, right? Linear systems, and then actually subjected to actually you look at the quadratic cost of functions, applied to subjected to this set of linear differential equations. The solution is convex optimization, and then you get the globally minimum point in a very few steps. So no, linear MPC is a convex optimization problem, no local minimum, and well, in our computation, more than 100 times faster, computation. It's not just a few times, 100 times faster computation compared to, nonlinear MPC. So, yeah, go ahead.
What's the difference between Koopman and DFL in this table?
Yeah, I'll explain that. Okay. Here, Koopman, what I did, and here, okay. But yeah, instead of using this particular set of observables, we use many observable functions which we created. But anyway, so first, comparison is made between DFL and the nonlinear optimal control. So the first one is mean squared error, basically computational performance, right? And then calculation time. So when we use the DFL, the mean squared error is 0.0364, and then even though you use the full scale nonlinear programming, applied to MPC, almost incompatible, error. But time for computations, this guy, nonlinear programming, about 80 times the longer time, and this one 200 times the longer time. So it's pretty actually, complex. Now, I also, we also compared this one with the Koopman, and Charles asked how I did the Koopman, how we did the Koopman computations. So here's the things. The process we look at is 8th order system like this, 2 masses, and then actually 4 masses and 4 springs, and 4 energy storage elements needing 8 state variables. And all the springs and the dashboards there are nonlinear, or nasty nonlinear systems. So, we use radial basis functions again, radial basis functions for observables. So observables is basically some functions of state variables, right? State variables. So the way I did and the way we did was basically, the first observable is basically, Gaussian function like this. And I know it's a function of x1 alone, okay? And then it covers only this area. And actually, for this area, we have yet another, Gaussian function G12, and as such, we use the 25, Gaussian functions to convert the x1 to, 25 observable functions. And then we have 25 times 8 state variables. So we use 200 radial basis functions for representing this actually creating the observables. So the total state is basically 200 eighth order systems. That's the ones that we did. Yeah, as a result, Koopman, the performance is not that good. Actually, I should include the more, radial basis functions, more observables need to be, added. And then actually the calculation time is longer. If this one is, more higher dimensionals, maybe one digit and higher, the dimensions, performance would be almost the same as the DFL, but the time required is almost 10 times bigger. So that's where we are. And then another interesting, point is that, lifted state feedback better informs the controller. What I mean by this is the following. For a linear system, feedback of additional variables does not make any sense, right? The state variable is it. That's a complete set of variables to locate the dynamic state of the systems, right? So no one really do additional feedback. But I know here for a nonlinear system, the use of auxiliary variables may better inform the controller. So in fact, the DFL MPC outperformed the nonlinear MPC. So not only just standard state feedback, and here we have some auxiliary variables, and we use this for the additional feedback. So what we did was basically here the lifted systems, right? So remember that we have extended the state variables from original x to x and eta, right? So likewise, we can actually expand this, this cost functional, this matrix, the Q, which is actually a positive semi-definite, matrix Q weight of this penalizing the deviations from the origins. That's actually penalized with this weight Q, right? So if you just focus on the original state alone and penalize that, you should use this one. Just left the top of n-dimensional n by n matrix Q. It should be used and set all the other part is to be 0, right? But interestingly, you also penalize the deviations of eta, from the origin with these additional weights, Q eta eta, Q x eta as arranged here, okay? That is actually basically, get the better results. Of course, with this actually, with this controller, LQR, solutions is include both actually state feedback XT and auxiliary, variable feedback. And in here, we include this guy. But this one that turns out to be very informative to guide the system towards the desired state more quickly. And here's the results. So shown here, and by the way, this we created a kind of a nasty program having bad spring constant and nasty vibration so forth. So here, Yeah, if you do not use the, that actually a full, Q matrix, just, using the an original, not the Q star, but the Q, yeah, you tend to do, deviate more, and then it takes a long time to converge. But, DFL with augmented the cost of functional, see this, shoot, it just, reach the, point very quickly, very quickly. So that's what we found to be very interesting. So, and then, in fact, the solutions to this, we solved nothing but just a linear LQR problem. Okay, just a linear LQR problem. It turns out that the result is this, cost of functional is basically a nonlinear cost of functional, right? Nonlinear cost of functional because eta is a nonlinear function of x. It's a nonlinear functional. And then actually a feedback is a nonlinear feedback, even though we use the linear schemes for, obtaining the optimal controls, but the net result is amazingly better. So the summary, quick summary of DFL, MPC, yeah, we, based on physical modeling theory, low dimensional lifted linear state equation have been obtained for non-autonomous systems. Oh, by the way, I just at the end, I cut the, case where auxiliary variables that include input U explicitly, therefore that's not the causal case. There's some careful treatment need to be made, but that story is actually eliminated from the talk today. But it's actually doable, and then actually physical modeling based method we can precisely find which variables are to be causal, which variables are not the causal. So that you should not use those variables for lifting. But anyway, so that kind of systematic method is available. So those observables are physically meaningful and it may be measurable. So you can put the say not only measuring the velocity, but also you can measure the force. And then actually, from the traditional sense, force and velocity. Are algebraically related, and actually there's no use to use both of them, but use other variables to be the auxiliary variables, and actually use that for lifting the dynamics. That's useful for actually linearizing the systems, also useful for controls. Okay, augmented the state feedback with the auxiliary variables can better inform the optimal controller. DFL is particularly useful for model predictive control for our limited, actually, finite time horizon, where DFL provides accurate, predictions. There are lots of related issues and challenges and open questions identified. So, has anyone thought about the lifting dynamics? Makes you a little bit uncomfortable as to observability and controllability. Yeah, controllability is definitely no, because it's basically bound to algebraic relations, right? So we cannot actually do that, maintain the controllability. But fortunately, optimal control does not require controllability. So that's actually good to apply this to MPC. And observability is a very critical requirement. Oftentimes it is difficult to measure both the independent state variables and auxiliary variables, observables, at the same time. Some variables are not directly measured, so you wish to construct the observer, right? So, combined with the observer, this may be interesting in the direction to go. And conversion of non-convex optimization to convex optimization, this is a big one. And even though, accurate nonlinear models, but it turns out that it's harder to find the global minimum for that nonlinear system. But if the problem can be converted to convex optimization, here we go. It's a very, very straightforward problem, right? And you have asked what is the actual approximation error, and that's a big question. I listed there at the end. Approximation error analysis is a big part, and that is still open question. Okay, so any questions up to this point? Oops. Yeah, okay. Oh, thank you. So, Bridget, I'll post the paper, the journal paper I published some time ago. Yeah. Oh, yeah, someone already posted. Thank you. That's so quick. Okay, cool. Okay, good. Yeah, just to conclude my lecture today. Yeah, yeah, conclusion of 2160, we are coming to the end. 2160, identification, estimation, and learning, right? So we emphasize the cross-disciplinary field of system dynamics, statics, and then machine learning. I found that this area is very exciting. Yeah, an emerging area. Surprisingly, these fields, they do not communicate, effectively, I would say. Interestingly, some of the terminology developed in one areas is totally differently called, but it's basically the same things and happening. And in many ways, at the interface between the multiple disciplines, is very exciting. And then, that's not the this not the in particular this statistics, dynamic systems, and machine learning. This area is very, very growing. And then maybe looking for the following 10, 15, or 20 years, this may be the major part of pushing forward. So system identification, state parameter, state and parameter functional estimations, and supervised learning. We call it differently, but it can be studied in a cohesive manner. This is another way of stating that the cross-disciplinary studies. So 2160, we try to put them together in a cohesive manner. Some part is very difficult to use the consistent notations, and for instance, and then you'll be confused. And then also we have to deal with the different topics, from A to B and B to C. So in many ways, it's very much ambitious subject. But the message I'd like to give you for your take-home message is that this area is so important, and building models and then representing a model in a more effective way is very crucial. And we are about actually seeing the new big breakthroughs, and maybe more data-driven and more data-driven ready representation of the dynamical systems. That may be the important part. And also at the end, we look at the kind of lifting the dynamics, and we use more variables than needed. But I know this one is combined with some sensor technologies to progress. Now people can place a sensor everywhere, and including the inside of the human body or the environment scattered around in the whole globe, right? So many sensors, so many measurements, so high density measurement can be obtained. How you really exploit such technologies? Somehow the theory side, the representation, the modeling side should be actually consistent with the large amount of data and then sensor measurements. So in some way, this lifting dynamics, my viewpoint is that it will be very effective, the tools for this actually, new era of data. So that is something I like to talk about in here. So it comes to an end, and I hope you will find the material to 2160 useful for some of your current work and then future work. So that's the end. Thank you. And then I appreciate your staying with me for every lectures, and it's very difficult to do, but I appreciate your contributions. That's it. Yeah.
Thank you.
Okay.
Thank you.
Yeah. Any questions on
Thank
the
you.
last part? What something yeah, I'd like to keep in touch with you, if that's possible. Yeah, I've been involved in many of the doctoral thesis committees, and many of them are students who took 2160 before. So I'm interested in the things that you've been doing, and if that is applied to some more important project, that's really fun things to me to see. Although and many other expertise are needed, but it's this is kind of bread and butter, right? Yeah, and then the most basic things to lift something. You can build many clever things on top of it, but the basics is something important. So that's all I need to say. Okay, so just in a few more busy days. Beyond that, it's nice time. So I hope you have time to relax a little bit. Yeah, and then fresh up, and we see from February, on campus or otherwise. Yeah. Take care. Bye.
Thank you.
Bye.
Thanks.
Bye.
Bye.
Thank you.
Thank you.